export button here. Right. Just to remind everyone, we have our, what do we call it? Physics and Physical Science seminar on Friday, right, by this guy, Jason. He's from CSU East Bay, and he actually works in Switzerland on this thing called a Large Hadron Collider in a field called particle physics, which is kind of like this, you know, the world kind of physics, but a lot of it, so this is where I worked on before I came here also. A lot of it is like running, you know, programming a computer to do stuff. And a lot of it is also like running pumps and valves, so you can actually have your coolants and your chemical in the right places so that they don't explode. And also controlling these valves and pumps electronically, so you can actually do it remotely as opposed to being right in front of it. And that way you can actually share the job, so you don't have to be there 24/7 to make sure your detector doesn't explode, and then so people can take shifts monitoring the detector, and also like there'll be a computer that can automatically shuts off the valve if, you know, something bad happens, right? So these are like safety systems. So if anyone's interested, there is remember the 20-point extra credit, and what else I was going to mention this week? Something I forgot about this week. Oh, well, there's also the Cowbridge thing, so anyone who's interested in doing graduate school in physics, astronomy, computer science, math, right? Chat with me or whoever your major advisor is. Say they also know about Cowbridge, okay? Let's see. Any questions from about magnetic fields for this chapter or other topics that we talked about before? I'm just going to keep scrolling. All right. So, no questions yet? Okay. Last time we talked about this thing called magnetic field, right? Magnetic field is created, let's have my little drawing up here, right? Let's say you have some charged particle with some charge Q, right? And it's moving at some velocity V, okay? So this is gonna, since this is a charged particle that's moving, it's gonna make a bunch of magnetic field in little circles around it. I think the book usually uses the color blue, right? So if I use my right hand curl rule, right, so the charge is moving in this direction, we expect the magnetic field to be kind of coming out of the board here, going all the way out, going back in the board, and coming back out. Okay, so what you can do is you can make these little drawing, right, where it makes it look like it's coming out of the board here, and then going into the board here, right, and then continuing on inside the board, right, kind of like this, right. Okay, but in general, you can actually calculate this magnetic field, not just perpendicular to it, but any point, you know, some point P. Let's do that in black, right? But the problem is that now you have to calculate this cross product, where this R is the vector between your charge and wherever you're interested in measuring your magnetic field, right? It doesn't have to be an object there, but if you were to put something that's magnetized there, it will be affected by the magnetic field, and we're going to talk about how magnetic field exert forces also on charged objects that are either moving or magnetized. So we're going to talk about what that is later on in the chapter. Probably not this week. Probably going to be after your midterm next week. Okay. Okay. But we can calculate this magnetic field here, right? And remember, magnetic field is symbolized by this symbol B, right? Right. And to figure out the direction, right, we use the cross product, where, you know, the magnetic field is actually a cross product between the velocity vector and the r hat vector, which is actually the direction, right, to r, to point P, right? So when you're doing a cross product, right, A cross B will give you whatever C is, right? In this case, The first vector we want is v, so we want my thumb to point in this direction, right? And then the r vector is going to be in this weird direction. But remember, right, this cross product only picks up the perpendicular part of the r vector, right? So therefore, you don't have to like point your finger like this. You just have to point in the part that's actually perpendicular to it, right? And what happened is that the magnetic field will point in the direction of your middle finger, right? So at this point P, in fact, it does come out of the board, right? So that cross, this, your right hand actually works that way. So, and to calculate the magnitude of the magnetic field, you well, also the direction technically, because this cross product is in there, right? You use this thing called the Biot-Savart's law, right? We just have this weird constant, mu naught, which is, I call it the magnetic constant. The book either calls it the permeability, the permittivity, something tivity, right? I call it the magnetic constant. So just think about it as the magnetic constant. Divide by 4 pi as usual, right? The charge, of course, is proportional to how much charge you have. How fast the thing is going. This r, right, is an r hat, right? It's the unit vector in this direction, right? So in this drawing, right, r hat will be like a r vector with a length of 1, divided by r squared, okay, is inversely proportional to the distance you are away from it, just like electric field, right? It looks very similar to electric field, except for this cross product thing that's going to be like kind of wonky to deal with, right? This is inherently like a 3-dimensional thing. So what I'm going to do, I'm going to do an example. It's just a very simple example. Let's say we have an electron, right, that's moving at 1,000 kilometers per second, a pretty zippy electron, along the y-axis. There you go. And what we're going to do is try to calculate the magnetic field at different points, right? Let's say r is equal to 0, 1, 0, right? So this x coordinate, y coordinate, z coordinate. Okay. So first of all, what we want to do to set up the problem is, well, I'm going to have my little charge, and the charge of this is actually negative e, right? Right. The charge of an electron, let's just call it QE. Charge of an electron, right, is negative 1.6 times 10 to the negative 19 coulomb. Okay. And the place where we're interested in calculating the magnetic field is the vector r. So this is 0 in the x direction, 1 in the y direction, 0 in the z direction. So let's call this my point P. Which color did I use for point P? Black. Right. This is our point P, and it has some r vector that's pointing straight out this way. Okay. And this electron is moving, right? It's moving along the y direction, right? So it's moving straight to that point. Okay. So before we do any mathematics, right? Remember that the Biot-Savart's law, right? One part of it is the cross product between velocity and the r unit vector, right? Without doing any calculation, can we figure out what the magnetic field is due to this one little charge at point P right away? If it is a cross product, and these are the directions of r and v. What do we think? What does the cross product do? It picks out which part of the two vectors. It tells you how perpendicular the two vectors are to each other, right? How perpendicular are the two vectors to each other? They're parallel, so there's no perpendicularity. I'm not sure that's a word, right? So right away you can actually just answer this question. The magnetic field here at this point is actually 0, and that's it. Okay. So look for this type of stuff on midterm, right? So before chugging in a bunch of numbers and doing a lot of work, right? Just look at the picture and understand that cross product picks out the perpendicular part of your vector. Okay, the two vectors to each other. So that's the simple example, right? The next one, well, hopefully it will not be 0, because that would be kind of boring if I just keep calculating zeros, right? The next one, we have the same charge of an electron, right? It's still moving along the y-axis at some velocity v, but now we want to calculate what is the magnetic field along the x-axis, right? Because that's x, y, and z. So let's say this is 1 centimeters, right? This coordinates is 1 centimeter. So r, right, is actually in this direction. Now, right, we don't have two vectors that are parallel to each other. Now we actually have to use the Beal-Savaart's law. Okay, the Beal-Savaart's law is that the vector thing itself, right, is this crazy constant, the magnetic constant, divided by 4 pi. Okay, the charge times the cross product between v cross r hat. This v is kind of funky looking, but hopefully you can see that's a v, divided by r squared. Okay. Okay, so remember the strategy when you're calculating these complicated cross products stuff, right? Just the same thing we did with torque. We try to figure out what the magnitude is first, okay? So remember the b without the arrow indicates it's just the magnitude of that vector, right? Not the whole vector itself. Well, of course, the magnitude of this, right, is just going to be q times v, right? The magnitude of a unit vector is just 1, okay? Right? To figure out the magnitude between a cross product, you multiply by the sine of the angle between the two vectors. Okay? Between the two vectors, right? Okay. And of course, r squared is already a magnitude, so we don't have to magnetize it, magnitutize it. Okay? So we know the charge. Let's just do some checks. We know the velocity, right? We know the magnitude distance, right? It's 1 centimeter. We know what mu naught is. We know what 4 pi is, right? What the heck is this theta? In this case, what is theta, right, on the drawing? 90. Right, because it's the angle between V and R, right? So that's a 90 degrees. So we know what that is. So that's actually 90 degrees. Okay, so this equation simplifies pretty quickly. Okay, you got mu naught, which is 4 pi times 10 to the minus 7. And it'll have some interesting units that ends up with Tesla. Okay, and then there's a 4 pi on the bottom. The charge is 1.6 times 10 to the negative 19. And of course, this is going to be a negative charge because that's an electron, not a proton. Okay. So, and then the velocity was 1,000 kilometers per second. That's actually 10 to the 6 meters per second, a million meters per second. Pretty zippy electron. And the distance to it is 0.01 centimeters, 0.01 in meters, right, squared. Okay. All right. Since this is the first time I'm writing, we're calculating this, I'm going to write the full units so that so we'll figure out how the units cancel out. So I have to look up the units for mu naught, the magnetic constant, which we talked about last time, is a Tesla meters per amp. Okay. Let's write that down since this is the first time we're calculating. All of this is in SI units, so it should all cancel out, right? Okay. All right, so now we just have to deal with a little bit of calculation, right? I'm gonna punch that in my calculator. Well, cool thing is that, right, these 4 pi's actually cancel out exactly, right? You don't even need to calculate these 4 pi's. Okay. 10 to the minus 7 times 10 to the 6, right? You get left over 10 to the minus 1, right? And therefore, what's up here is actually going to be 10 to the minus 18, right? Oh, sorry, 20. 10 to the minus 20, right? Because basically 10 to the minus 19 times 10 to the minus 1 is 10 to the minus 20. You're adding those two numbers. Am I doing that in a crazy way? Okay. You can also punch this in your calculator. You'll get the same thing, okay? All right, so on the numerator, right, it's actually negative 1.6 times 10 to the negative 20. And we have units of Tesla meters, right, per second. And then this is Tesla meters per ampere. And then we have a meters, and then we have a coulomb here, right? We have a meter here, we have a second here, and then at the bottom we have meters squared. Okay? And then this is all going to be divided by 0.01 squared, which is 0.001, right? Whew. Okay, so this is essentially 10 to the minus 4, right? 10 to the minus 20 divided by 10 to the minus 4 is actually 10 to the minus 16, right? You're subtracting the difference when you're dividing, okay? And now we end up with these crazy units here, right? Luckily, right, there's a meter here, and a meter square, right? So those go away right away, okay? But then the rest of the units is a Tesla divided by ampere and a coulomb per second. So how did those cancel out? You guys remember? What's the... Because we should only end up with Tesla, right? That's the units for a magnetic field. What's a coulomb per second? And, well, yeah, it's a charge per time, right? And ampere is basically a charge per time, right? Because this is the units for current. Remember, a current is how much charge is flowing through a place per time, right? So this is actually the same thing as an amp, so the amps actually cancel out, right? And therefore, the magnetic field right there is actually negative 1.6 times 10 to the negative 16, okay? Right? That's not the end of it, right? Because that's just the magnitude of it. In fact, right, we actually don't really care about the sign that much. Because what we're going to do is we're going to use our right hand to figure out what the direction is, right? Right? The Biot-Savart's law is that it's V cross R, right? So if it's a positive charge, it will go into the board, right? But if it's a negative charge, which way should it go? It's coming out, yeah. So the magnetic field direction is actually coming out of the board, so you will actually draw it like this, right, this point, okay? And that's actually along the negative Z direction, right? It's coming out of the board. So the full answer at the end, I'm going to erase this a little bit, okay? Right? Make this into a vector, and the direction for Z direction is K hat, right? So this is the full answer, right? Because the magnetic field's in the negative Z direction, so this negative sign actually takes care of that, right? And this is the negative K hat direction, and the magnitude is 1.6 times 10 to the negative 16. Okay? Not so bad, right? Do the magnitude first, figure out the direction after, okay? Or the other way. You can do it either way. They're pretty decoupled from each other. All right. You guys ready to do a harder one? All right. Okay. Same charge. Keep repeating this. And some velocity v going along the y-axis, right? But now we're not going to have this perpendicular thing to it, right? And the coordinates is going to be 1, 0, 1. That means the x coordinates is 1. So let's do that in black. 1 centimeter. The z coordinate is also 1 centimeter. So it's actually the cross point between these two places. Okay. This is where we're trying to figure out what the magnetic field is. Okay. All right. Okay. Okay. So, right, once again, what we're going to do is we're going to apply the Biot-Savart's law, right, where we try to figure out the magnitude first, right, mu naught over 4 pi q times how fast the thing is moving, right? I'm just copying this equation, right? Okay, oops. Right, we're going to have to figure out the sine of theta thing, though. Okay, times 1 times sine of theta, right? And this is going to be divided by r squared, right? Okay. So luckily, right, since this is still on the xz plane, this angle here is still 90 degrees, right? Right, so this is still going to be 1. Okay, but this distance r, right, is not 1 centimeter anymore. What is it? How do we figure out what the distance is? If this is 1 centimeter, this is 1 centimeter, what's r? If you have a triangle, I'm sorry? Pythagorean theorem, right? So 1 square plus 1 square equals to the hypotenuse square, right? So that's actually going to be r itself is going to be 1 centimeter square plus 1 centimeter square, right? All square rooted. And this is going to be square root of 2, and the units will come out to be centimeters, but we're going to convert that to meters. So it's going to be square root of 2 times 10 to the negative 2 in meters. Okay, so we're going to plug that in over here. Okay, the rest of the equation is the same. Okay, okay, where mu naught is going to be 4 pi times 10 to the negative 7 This time I'm not going to do units, right? We know that units will also work out if we put everything in SI units, right? Negative 1.6 times 10 to the negative 19 coulombs. The velocity is 10 to the 6 meters per second. The distance, right, this squared, right? So it's actually square root of 2 times 10 to the negative 2, the whole thing squared, right? Right? And therefore, this magnitude here is actually going to be, this cancels out, this partially cancel out to 1, this gives you the 20, this gives you the negative 4, right, because this distributes to both, okay? So it's actually going to be negative 0.8. Okay, let me do it in 2 steps, sorry, okay? So that combines to 20, so on top we have 1.6 times 10 to the negative 20. Okay, on the bottom, right, this square goes to both of these, right? So square root of 2 squared is just 2, and then negative 10 to the negative 2 squared is 10 to the negative 4. Okay, so these subtract out to negative 16. Okay, 1.6 divided by 2 is 0.8, right, times 10 to the negative 16. Okay, and then we'll move the decimal over to make it look nice. That's 10 to the negative 17. Okay, that's the magnitude, right? Now we have to figure out the direction, right? Okay, right? The direction is going to be a little bit funky, right? Because, right, when I do V, right, using my thumb, cross R, right, there's actually a X part that's going to be perpendicular to V, and there's also a Z part that's perpendicular to Z, right? Okay. In fact, what's going to happen is that you're going to have a magnetic field, oops, if I go, that's kind of going, magnetic field at this point is going to be going at this, well, since it's a negative charge, it's going to be coming out like this. That's the direction of the magnetic field. So the magnetic field is going to have some X component going this way and some Z component coming out, okay? In fact, since this angle here is, I'm not going to call it theta because I already have a theta, phi is 45 degrees, okay? If you want to vectorize this magnetic field, right, it's actually going to be whatever the magnitude is, right, whatever this number is, right, times cosine of 45 degrees in the x hat direction, which is I hat, right? And then since we know it's coming out of here like this, right, it's going to be in the z hat direction for this z direction. So it's going to be the magnetic field times sine of 45 degrees. I mean, it doesn't actually matter since sine of 45 and cosine of 45 is the same number. But in this case, we should, you know, in this case, it doesn't matter, but we should keep it like that, okay? So, and if you punch this number in, so I don't actually memorize what cosine of 45 is, e to the negative 17 times 45 sine, okay? Whoa, why is this number so big? Doesn't make sense. Times 45 sine, okay? It's going to be 5.7 to 2 sig figs times 10 to the negative 17 in the I hat direction. And then since this is an, ooh, I did this wrong, right? It's not in the J hat direction, right? Looking at this drawing, right? The magnetic field is coming out of the board, right? So it's actually in the K hat direction, right? Okay. Since this negative sign is there, let's just change it into a subtraction sign between the two. And the calculations, since sine of 45 happens to be the same as cosine 45, you get the same value here, okay? And that's actually the full vector that you get, okay? Right? Okay. A lot of vectors, right? But then once you kind of calculate the magnitude, right, you want to figure out the direction using your hands, basically, okay? Okay, I'm going to try to get to the first example that we need in order to do the worksheet today in about 10 minutes. That way I give you guys at least 20 minutes to work on the worksheet today. Okay, and today's worksheet is going to be, well, now we figure out the magnetic field created by a single charge, right? Usually you just don't have a single charge flying around, right? You have a lot of multiple charges running around inside wires, right? And this is called current, okay? So if you have a current that's moving through a wire, it's essentially, just picture it as positive charges moving through that wire, right? We know in reality it's negative charge moving in opposite direction, but it's the same thing as positive charge moving in the forward direction, right? So what we can do is modify Biot-Savart's law and make it into the version that we want in order to calculate what the current is, okay? So if you take a little chunk of your wire, right? This little chunk of wire has some amount of charge delta Q. Let's not even do the QI, right? And the amount of charge that's moving through here, right, per units of time, that's actually what current is, right? Okay. So therefore, what you can do is convert this amount of delta QI times the velocity, right, which is what's in Q times V up here in the original Biot-Savart law. And you can do a little bit of, delta, right, where V is actually the change in position over the change in time. Remember this S is just some arbitrary direction, right? It can be X, Y, Z, right, or somewhere in between them, okay? Then what you do is you move this delta T under the delta Q instead, and now we have delta T over delta T, which is actually what current is, right? So the charge times velocity is actually the same thing as current times a tiny displacement vector, right? Delta S is just some motion, right, along a arbitrary direction, right? Delta S from some initial point, S final, to from some S initial, okay? So therefore, we can modify Biot-Savart's law for a tiny current segment, right? The mu naught over 4 pi is still there, right? But instead of Q times V, now it's the current times a little bit of delta S, okay? We still have to deal with this vector stuff, but now we can quantify it in terms of the current. Of course, this 1 over r squared is still there, and we still have this r hat thing, right? So just to picture this, right? So instead of just a single charge that's moving, right? If we have a current moving along this wire, right? This will have some current, and then the direction is quantified by this little delta S, right? This is a vector, right? And then r hat, right, points from where the current is to where you want to measure the magnetic field, and I keep calling it point P, right? In fact, right, if you actually just do this using your right-hand curl rule, right, we know that the current is going this way. By the time the current reaches here, we expect the magnetic field to be coming out of the board, right, which is exactly what we will see if we do the cross product, okay? So I'm going to show you guys a, this is going to be the hard example, and you guys are going to get to do another one that hopefully is simpler in the worksheet. And this is example 29.3 in the textbook, and we just want to go over it, okay? Where, let's say we have a long wire that has some current I going through it, okay? And we're going to point this wire in the positive X direction, just to orient ourselves, okay? We're going to find the magnetic field at some point P distance away from the wire, right? Some up here somewhere, okay? Right? So the geometry is that we're going to have some, instead of delta S, right, since the wire is going only in the X direction, right, we're going to have delta X instead, okay? So what we're going to do, I'm going to start writing down the current version of Biot-Savart's law, okay? Let's write it down over here, right? So it's going to be a tiny segment, how do you spell segment? SG, yeah. Right? The mu naught is still there, the 4 pi is still there, right? Instead of charge, we have current. Instead of the velocity, we have this delta S cross producted with r hat, all divided by r squared, okay? Right? Since this is only in the X direction, we know that delta S is going to be basically just delta X, the vector, right? Since delta X is the vector, we're just going to put delta X in the I hat direction, right? Okay, okay. And the I hat direction cross producted with R hat, right? So 1, right, your thumb, and then we're going to find the perpendicular part of it, right? The perpendicular part of R hat is actually, well, the part that's pointing straight up. So we expect the magnetic field to be coming out of the wire here, right? Which is what you expect, right? If you just do the regular current curl rule, so there's 2 different right-hand rules, right? There's one with the fingers, and there's one with just the curve, right? We expect the magnetic field to come out here, which makes sense, right? So let's say we expect the magnetic field to come out, okay? So it will only have a negative z direction, okay? So once again, we're going to try to figure out the magnitude of this first, right? I kind of did the direction already, but how do we figure out the magnitude, right? So the magnitude of this, right, is going to be, let's call that Ts, right? The current times a little bit delta xs. Instead of delta s, it's going to be delta x instead, of course, right? Because the wire is only moving, it's only in the x direction. Times 1, so because that's the magnitude of r hat, right? So this is an x, not a cross product. Unfortunately, they look very similar. Okay, times sine of the angle between them, right? Once again, just like before, and then r squared somehow. Okay, right? The angle between them is going to be more complicated because at this point the angle is this, right? Okay, but at, you know, let's say you're going to be adding up like a different part of the segment, the angle changes, right, depending on where you are on the wire. So the angle is actually the variable now. Okay, so the way you can quantify this angle is that, well, I know what this angle is, right? Because it's actually, well, I know what sine of theta is actually, because it's the opposite over the hypotenuse of that angle, right? So the opposite is y, right? The hypotenuse is the distance r. So sine of theta is actually y divided by r. Okay? This I delta x. I'm going to skip the 1 because we're multiplying by 1. It's just going to be 1. And then instead of r squared, we have r to the 3rd power, right? Because the sine of theta gives you an extra factor of r to the 3rd. Okay, so how do we deal with this? Okay, so this is the magnetic field for a little tiny segment, right? Delta x amount. Okay, what we need to do, right, is basically integrate this from from negative infinity to positive infinity in order to calculate the total magnetic field. Okay, so what I'm going to do is I'm going to sum up all the magnetic field from the tiny segments, right? Right, and that will give me the total magnetic field, at least the magnitude, right, from the entire wire. Okay. Okay. So if we have this summation here, mu naught 4 pi the current delta x y and then r to the 3rd, right? What's going to happen is that, you know, these are constants, right? The stuff I'm going to highlight in yellow are constants, so we can pull that out of the summation. Okay, so mu naught I 4 pi y is also a constant. R is not a constant, right? Because as you can see, right, as we get closer to point P, R actually decreases, right? That's the distance between the wire and point P. Okay, so we're going to have a summation of delta x, and we have to find a way to quantify r to the 3rd power, right? R is this distance, right? Right. So using Pythagorean theorem, y is actually r is actually y squared plus x squared, right? Well, square rooted. Okay. So what's down here is actually y squared plus x squared to the 3/2 power. Whew. Okay. The next step is then to make delta x a small, you know, an infinitesimal amount, and therefore, right, this turns into an integral. I'm going to have the same constant out front. Okay, there's going to be dx, right, and going to be I'm going to write it in this order. 3/2 power. Okay. We actually done this integral before in chapter 23. Okay, so that's the magnetic field of the entire wire. Okay, we've actually done this integral before, and you don't have to memorize it, but what's going to happen is that you're going to have an extra factor of x on top, and this power is going to get reduced by 1 y squared to the 1/2 power instead. Oops. Okay. And then there's going to be an extra factor of y on the bottom. Okay. So the y actually cancel each other out. Okay. And we're evaluating this from negative infinity to positive infinity because we have a very, very long wire, right? Okay. So I think this y is up here. Sorry. Now I have to look up that integral. Sorry. This was from chapter 23, which was lecture 6 or something. So I want to double check that integral. Right. Where did we do this? Okay. Right. What a mess. This integral. Okay, yeah, so it's y, the variable, divided by d squared. Okay, sorry about that. The variable, in this case, is x divided by this square, y squared. Okay, so actually one factor of it cancel out. Okay. Okay, so trying to evaluate this from negative infinity to positive infinity. Okay, so x over x squared plus y squared, right, minus 1/2, right? So at either positive or negative infinity, basically this term will dominate this stuff in the denominator, right? And then, but then it's square rooted, right? So if you put in negative infinity here, right, it's negative infinity squared, and then you have a positive infinity up here, right? But then this whole thing is square rooted, so they actually cancel out, and the limit actually goes to 1, right? Right, which is kind of funny. Okay, so at the end here, this whole thing, if you evaluate from positive to negative infinity, you end up with a factor of 2. Okay, 4 pi times, right, 1 plus, well, 1 minus negative 1, basically. Okay, because this limit goes to negative 1, the other limit goes to positive 1. Okay, so this is actually going to be mu naught I over 4 pi y, oops, forgot the 2, of course, so this goes to 2, so it's actually 2. So that's the magnetic field of a wire, right? And the vector of it is going to be coming out of the board, which is in the negative k hat direction. Okay. Okay. Right. And the picture of it will look like these. Okay. Where it's just kind of a magnetic field going around a wire, as we expect, right? Just by using our curl hand, right? But this also gives you the magnitude, right? Right. It's inversely proportional to r. Huh. So that's exactly what you're going to do on the worksheet today. I'm thinking we only have 10 minutes, so you're not going to be able to finish that. Is it okay if I just kind of move on to the next section and then maybe start with a worksheet tomorrow instead? Okay. All right. Well, before I move on then, any questions about this? Right. A few of you guys had trouble with this on the first midterm, right? I don't think there's going to be a version like this on the second one, but this is going to be on the third, right? Right. Right. A lot of the strategy is that, right, these Biot-Savart's law or the Coulomb's law and all that stuff, right, you can calculate what they are on like a tiny amount of charge, right? So I know exactly how to calculate this if I have a tiny amount of charge or tiny amount of current here, right? But if you want to make it for an entire wire, you have to add it all up, right? So you have to have a very good function to define what it is here, and then you basically do an integral to add up all the rest of the wire, and then that's where the integration comes from. Okay. All right. All right. There are more examples in the textbook. There's of course our worksheet that we're going to do. So this is another wire one, a straight wire one. There's actually also magnetic fields inside a loop. So if your wires, instead of going in a circle, it'll create a magnetic field that's actually going to be interesting. You can actually figure out what the direction is by just using your right hand. So let's say we have a loop here like this, right? We know that the current is going to go this way, and no matter which part of the circle you're on, the magnetic field is always coming out of the board here, right? So we can actually instantly know what the direction is, right? It's going to be going into the board outside, okay? But you need to do all that integration to calculate what the magnitude is, right? So that's the key thing, okay? And in fact, here's the answer, right? It looks like this funky thing, and the example takes you through the mathematics to calculate that, okay? The interesting thing is that for a ring like this, right? This is the exact solution, right, as a function of the radius of the ring and the distance out, right? Just as we did with electric field of a ring, we try to simplify it, right? What we do is that, well, if we're interested in the magnetic field exactly at the middle of the ring, that means this is z coordinates, right? We reduce that to 0, right? If z goes to 0, what's going to happen is that, right, this r square, right, we're going to take that to the 3/2 power. That means essentially it's just r to the 3rd power, right? And then that cancels out partially with the r on top. So the magnetic field inside a loop right at the center, right, of that loop, not where z is equal to 0, is actually just this mu naught once again, right? Even the pi's disappear, divided by 2, okay, from the, I think, the limits of the integration. The current divided by the size of the loop. It's a pretty simple formula, okay? And the book will take you through all of this, okay? And this creates these interesting devices called solenoid, where you can actually create a pretty strong magnetic field by coiling a wire over and over and over again, because each of these loops contributes this amount of magnetic field. So if you have, you know, let's say 1, 2, 3, 4, 5 loops here, you multiply this by 5, and you make a bigger magnetic field, okay? So we're going to talk about how we can actually derive this next in a Thursday is the review, maybe tomorrow, okay, when we actually do what's called Ampere's law, okay? But you can actually calculate what is the magnetic field inside this loop right now, following the example up here with the ring, right, where we take z equal to 0, right? It's just going to be exactly what we had up there, but then you multiply by the number of turns, okay? This n, capital N, is the number of turns in that loop. So if you loop this, you know, over like 1,000 times, then you get a magnetic field that's 1,000 times stronger, right? If you loop it only twice, it's only twice as strong, right? And then we're going to have a half ring version of it, and we'll figure out how big that is, okay, tomorrow when we try to figure it out as a group. Okay. Since I'm kind of buying for time before tomorrow's lecture anyway, I'm going to talk a little bit about magnetic dipole. I mentioned that this is not going to be, I didn't assign any homework, and also it's not going to be on an exam, okay? So if you guys want to stop paying attention, this is the time to do it, okay? But magnetic dipoles are interesting because we actually just kind of talked about it, okay? So if you go back up to this ring situation that we talked about, right? Okay. The thing is that inside, in the middle here, right, the magnetic field, if the current is going this way, right, if I point my finger this way, right, the magnetic field is actually coming straight out of the ring, but then it kind of curves around here, right? And we can actually have a little drawing of this. This is what this drawing down here is trying to draw, right? This is the side view of the ring, okay? The little dot here indicates that the current is coming out here, and then imagine the other half of the ring coming out and then going into the board like this, okay? Okay? And this is what the magnetic field line will look like if you have this projection, right? So once again, I can use my thumb to figure this out, right? If I have a current that's coming out here, right, I expect magnetic field lines to be going around a circle like this, okay? If I have a current that's going in, right, I expect a magnetic field line to be going around like this, right? Notice that the current coming out and the current going in, they both have magnetic field that goes in the same direction on the inside, right? Which is sort of neat, okay? So now if you turn this ring flat once again, right, you can see that the magnetic field is going to be coming out of the page inside the ring and into the page outside the ring, okay? In fact, if you take a picture of it, so this is actually a real ring, okay, where they place some magnetizable material, what's going to happen is that the magnetizable material will line up along the direction of the magnetic field line, and you can actually see this picture. Okay. So what's interesting is that, wow, interesting to me, but you guys can may not find this super interesting, is that this field line configuration is exactly the same field line configuration if you have a permanent magnet. So somehow, current going around in a circle seems to indicate there's something about permanent magnets that is similar. Okay, and that's the thing I want you guys to get out of this section. Okay, just the concept of this, that somehow, right, permanent magnet, it seems like there's stuff going around in a circle. Okay, and we're going to talk, we're going to figure out what that is at the end of towards the end of the chapter. Okay, some applications of current going around magnets, there's a lot of them. So anytime you have a motor, right, so like the fan inside our computers, even the buzzing, the vibration buzzer on your phone is actually a little tiny motor, right? Those uses electromagnet to create a magnetic field inside another permanent magnet. Therefore, the two magnets actually repel each other, then attract each other, repel each other, attract each other, and it makes this circular motion. Okay, and we're gonna see that later. Okay. Yeah, let's not deal with the equation of the dipole, but the thing I want you guys to take away is that things going around a circle seems to have something to do with permanent magnets, okay? That's all. All right, so let's end a little early, and then we'll start with the worksheet tomorrow.